Hi, I'm Dr. Prathana Ghosh, and today I'm going to talk about double integration method theory to compute slope and deflection at any point in a beam. So what is our lesson objective today? Actually, to determine slope at any point in a beam, which is theta, and determine vertical deflection at any point in a beam. And we'll also measure the sign convention of slope and vertical deflection. So first, we need to know what is the importance of finding deflection in a beam. So let's talk about that. So if you see the picture here, we have a simply supported beam, pin and roller, and we have one uniformly distributed load, W per unit load acting on the beam. So due to action of this load, after a certain amount of time, the beam will deflect, as you see the deflection. So the beam will have maximum deflection, V max, exactly in the middle of the span. So this heavy deflection could initiate failure of the beam if it exceeds the allowable limit. So our aim as a structural engineer would be to compute the maximum deflection and make sure they are within allowable limit of deflection. Otherwise, the beam would initiate cracking and eventually failure could happen, specifically in reinforced concrete beam. Being said that, so one of the things we need to know when you need to compute slope and deflection by double integration method, we need to know the elastic curve because beam elastically deflate under the action of the load. As you see some of the pictures on the right side, due to the action of the concentrated load P, we have one side pin, the other side fixed, it deflects under the application of the load. Similarly, if you have overhanging beam with pin and roller support, if you have concentrated load exactly at the free end or overhanging end, you see that end deflects downward, the other side it will start to move upward. So you can do this basically imagination by using a pen and pencil so that you can see how you can bend the paper with paper and pencil and see the deflection curve. So we can imagine that that elastic curve is one of the deflection curve of the longitudinal axis that passes through the centroid of each cross-section area of the beam, which we can define as elastic curve. So we can imagine that there is some connection in between the bending moment and deflection curvature because the load creates some bending moment in the beam and that bending moment will create some amount of deflection in the beam. So if it is related with each other, and that's how the double integration theory has been developed. So double integration theory is expressed by following this moment curvature relationship. What is the relationship? It is given in the equation EI d2v dx square is equal to m. What is EI? EI is the flexural rigidity. E is the modulus of elasticity of the beam. I is the moment of inertia of the beam. And V is the vertical deflection. And X is the, at generic distance X, we are basically cutting and we are trying to compute our moment. So moment is the, M is the internal moment developed in the beam. So we'll go through an example problem to find out slope and deflection at particular point in the beam. What is the example problem? Here is that example problem. As you see, we have a cantilever beam, one side fixed, the other side free. And we have one triangular loading W per unit length exactly acting in this beam throughout the beam. So our aim will be to find out slope and deflection at free end of the beam, which is this end. So we need to find out this vertical deflection V as well as slope in the beam. So what do you do? Basically, first step will be to find out the moment developed at a generic distance X. So why we are calling this double integration method? As you see, if we integrate, our equation is EI d2v dx square is equal to m. So if we integrate first time, the left side and the right side, we'll get the slope. Slope is equal to theta, which is dv over dx. So integration of d2v dx square is equal to dv over dx, and dv over dx is the slope of the curve. Again, if you integrate one more time, which is the second time, then you will obtain vertical deflection. So first integration, you see EI dv over dx is equal to integration of m dx plus c1. This dv over dx is called as slope theta of the elastic curve. Then again, you are integrating second time, and we are obtaining EI v, where v is the vertical deflection of the beam. That's why it is called double integration method. First integration will give you slope. Second integration will give you vertical deflection. And we are also obtaining two integration constant, C1 and C2. So those are unknown initially. So when you need to compute actual deflection or actual slope in the beam, we need to find out those two unknowns, C1 and C2. So how we are going to find out those two unknowns? By applying boundary conditions for the beam. So let's see what is the boundary condition for a beam with different support condition. So here is the table 12.1 from your RC Hebeler book that provides the boundary condition of the beam. So if we see very carefully, what we are seeing, if you have external roller support, what is the boundary condition? We know that roller support has vertical reaction. So that means there is no way it can deflect vertically. So delta is going to be 0 or V is going to be 0. So some books has delta as vertical deflection, some books has V as vertical deflection. Both are same. So please don't be confused with that. So as we see that we have external pin support, same thing. Our vertical deflection is going to be 0 because we have the reaction. If we have internal pin, again, vertical deflection is going to be 0, basically. If you have fixed end, then your slope and vertical deflection both are going to be 0. Why? Because fixed end is kind of a wall. So you cannot rotate a wall. That's why there is no slope. Theta is going to be 0. You cannot vertically deflect a wall because you have the reaction. You have all reaction, vertical reaction, horizontal reaction, as well as moment. So it's highly rigid support. So both slope and deflection is going to be 0. Whereas if you have free end, the last one, that means it can deflect, it can rotate. So that means we have no shear and no moment, no shear and no moment. That's why it can deflect and rotate easily. So now our aim to solve this example problem, to find out slope and deflection at free end A of the cantilever beam using double integration method. And it has been mentioned that EI is constant, which is the flexural rigidity is constant throughout the beam. So let's solve this problem in Microsoft OneNote. So I'm going to unshare this and I'm going to open Microsoft OneNote to solve this problem. So let's solve the problem. We have cantilever beam. With triangular loading. The height of the loading is W, A and B. Your length of the beam or span of the beam is L. And our aim to find out how much is the vertical deflection at A and theta A. Slope and vertical deflection at free end of the beam. So first step, to find out the internal moment. So applying the double integration elastic curve equation, EI d2v dx square is equal to m, which is function of x. We are going to cut at a distance x. We need to find out our moment equation, and then we'll apply the double integration theory step by step. So let's do that. So what is our new free body diagram? We are cutting at a distance x. We need to find out our new height of the loading. So now span becomes x, generic distance x. And what is the new height of the loading? By similar triangle, W over L times x. So what is our new equivalent triangular loading? Just a second. Area of the triangle, half W over L times X, base is X, and distances from the cut section is X over 3. And we are trying to find the moment at the cut section. So let's apply statics equilibrium equation. Summation of moment at cut section is 0. M counterclockwise positive, half W over L X times X, and distance is X over 3, which is creating counterclockwise moment. So if you see, we are obtaining our M is equal to negative WX cube over 6L. That's very important parameter because we are going to apply that in the elastic curve equation. So now let's go through our elastic curve equation. EI d2v dx square is equal to negative wx cube over 6L. So if we integrate one time, we'll obtain slope EI dv dx. EI is constant, so outside of the integration, and this one will be wx cube over 6L plus C1. So what we are obtaining? EI dv dx is equal to wx4 over 6 times 4, so 24 L plus C1. Integrate second time. EIV, vertical deflection, now we are obtaining. And once we integrate, it becomes C1x plus C2. So EIV negative WX5, 5 times 24, 120L plus C1x plus C2. This is your equation for slope and deflection. So equation 1 for slope, equation 2 for deflection. So our aim to find out slope and deflection at the free end. So basically V and dv dx, which is equal to theta, basically, by solving those two boundary conditions. So how do you solve the boundary condition? We know that when, if you see the very carefully the problem, when x starts from A, so when x equal to L, your slope is going to be 0, theta is going to be 0. When x equal to L, your vertical deflection is also going to be 0, because we know this is a wall, fixed wall. So let's plug it back. Boundary condition, x equal to L, dv dx is going to be 0, theta is going to be 0. X equal to L, v is going to be 0. So if you plug in equation 2, x equal to L, so left side is 0, x equal to 0, x equal to L, v equal to 0, so negative W L5 over 120L. So this one will be gone. You're obtaining C2 XC1 L So this is your equation 2. Similarly, this one, if you plug it back in here, in equation 1, what we are going to obtain, if you see very carefully, our equation, left side will be 0. And on the right side, we are obtaining WL4 over 24L plus C1. So C1 becomes WL cube over 24. Correct? Then we can find out our C2. So let's do that. First, we find out our slope. Our equation is EI dV dx is equal to Wx4 over 24L negative plus C1. So let's put the EI on the other side. dV over dx is equal to 1 over EI. Negative Wx4 over 24L plus C1. C1 is WL cube over 24. We are trying to find out dV dx, which point? At x equal to 0, which is A, theta A. We'll plug it x equal to 0, so this portion will be gone. So we are obtaining WL cube over 24 EI. We got positive value, so that means it is going counterclockwise. So we know that sign convention wise, if your slope is coming out positive, then it is counterclockwise. If slope is coming out negative, then it is clockwise. So now is our time to find out vertical deflection. So let's put it back here. Find out our C2. Zero is equal to negative WL5 over 120L plus C1L, which is your WL cube over 24 times C2. So if you find out C2, it will be WL4 over 120 minus WL4 over 24. If you simplify, it becomes 4 WL4 over 120. So it becomes WL4 over 30. Now we'll plug it back in our equation 2. EI V. Remember the equation, the original equation. Negative Wx5 over 120L plus C1x plus C2, correct? And our aim to find out the vertical deflection. So take the EI on the other side. Negative Wx5 over 120L, C1x, and C2 we got WL4 over 30. So our aim to find out vertical deflection at x equal to 0, which is at A. So that means we are going to put the x equal to 0. So this will be gone, this will be gone. Only thing is remaining WL4 over 30 EI. And this is negative, so that means vertical deflection is going downward. So vertical deflection, if it is negative, it is downward. If it is positive, it is upward. So that gives you the idea to apply double integration theory to compute slope and deflection at any point in the beam. Now I'm going to stop sharing this portion, and you'll have one practice quiz problem which I'm going to share it to show you. So let's go for practice. So this is your practice quiz problem. We have again simply supported beam, pin and roller, and one side you are having only one external moment is acting, M0, which is at the external roller support. And you have to find out basically the deflection at the center of the beam and slope at point B by using double integration method. EI is constant. I hope you enjoyed the video and you can apply double integration theory easily.